Two insulating small spheres are rubbed against each other and placed 1 centimeter apart. If they attract each other with a force of 0.1 Newton, how many electrons were transferred from one sphere to the other during rubbing? So here, this separation is 1 centimeter. One sphere is here with charge Q, another sphere is with charge Q. And charge will be opposite in nature because there is attractive force, and this force is given as 0.1 Newton. We apply Coulomb's law, so 0.1 equal to Q1 Q2 divided by 4 pi epsilon naught r square. So 1 upon 4 pi epsilon naught r square can be written as 9 into 10 to the power 9 into charge Q square divided by separation is 1 centimeter, that is 0.01 meter squared. So this will give Q square equals 0.1 into 0.01 square divided by 9 into 10 to the power 9. So this will become Q square equal to 1 upon 9 into 10 to the power minus 14. If we take square root, so we will get Q equal to 1 by 3 into 10 to the power minus 7 Coulomb. Now, we know that Q is equal to Ne, where N is the number of electrons and E is electronic charge. So we apply here, so 1 by 3 into 10 to the power minus 7 equal to N times 1.6 into 10 to the power minus 19. So N will be equal to 10 power minus 7 divided by 3 into 1.6 into 10 to the power minus 19, which will become 1 upon 4.8 times 10 to the power 12. So this can be written as 10 upon 4.8 into 10 to the power 11, which will be roughly equal to 2 into 10 to the power 11, which is our answer. Consider next question. Question number 13. NaCl molecule is bound due to the electric force between the sodium and the chlorine ion when one electron of sodium is transferred to chlorine, taking the separation between ions to be 2.75 into 10 power minus 8 centimeter. Find the force of attraction between them. So we apply Coulomb's law. F equal to 9 into 10 to the power 9 into charges, 1 electron. So it will be 1.6 into 10 to the power minus 19 whole square divided by separation is given 2.75 into 10 to the power minus 8 centimeters. So it can be written as minus 10 meters, then whole square. So it can be simplified. So 9 into 1.6 into 1.6 divided by 2.75 into 2.75 times 10 to the power. This will become 10 to the power minus 9 if we calculate this. So if we simplify, we will get 3.05 into 10 to the power minus 9 Newton. Let's go to next question. Question next is find the ratio of electric and gravitational force between two protons. So Fe, suppose they are placed at certain separation. So it is R. So Fe will be 1 upon 4 pi epsilon naught times Q divided by R square. So that is 9 into 10 to the power 9 times 1.6 into 1.6 into 10 to the power minus 38 divided by R square. This is equation number 1. Now gravitational force Fg is equal to gravitational constant. Here we are going to apply F equal to G times m1 m2 divided by R square. So this is 6.67 into 10 to the power minus 11 times product of the masses proton 1.6 6 into 10 power minus 27 into 1.66 into 10 power minus 27 divided by r square. If we divide the two, so Fe upon Fg. So we put the values. So it will become 9 into 10 power 9 into 1.6 into 1.6 into 10 to the power minus 38 divided by, this will become 6.67 into 1.66 into 1.66 into 10 to the power minus 27 minus 27 minus 10 to the power, sorry, minus 11. So if we simplify, so it will become 23.04 divided by 18.37 into 10 to the power minus 29 plus 65. So this will come out to be 1.254 into 10 to the power 36. Let's go to next question. Suppose an attractive force F equal to CE power minus KR upon R square X between the protons. Find the units and dimension of C and K, taking K equal to 1 Fermi power minus 1 and separation between two protons is 5 Fermi. Find the value of C if a repulsive electric force between the two protons is equal to attractive nuclear force. So here F equal to CE power minus KR divided by whole divided by R square. Here this is a number, so only this term e to the power minus KR will be equal to number. It means dimension of KR must be unity. So dimension of K or unit of K will be 1 upon R. So unit will be meter power minus 1 and dimension will be L power minus 1. And now consider this. So here, if this is unity, if we take this E as a number, in that case, no dimension is needed. So here, so F times R square equal to C. So C will be Newton meter square. And in that case, if we put the dimensions ml t power minus 2 into L square, then we will get ml cube t power minus 2. So we have got the unit and dimensions of K and C. Now, next part is to evaluate the force between two protons in this case, and then we have to find the value of C. So for this, values are given K equal to 1 Fermi. So we write it K equal to 1 Fermi minus 1, and R is given as 5 Fermi. So if we put the values, so we will get it as F equal to C e to the power minus K is 1, R is 5 divided by R square, 5 Fermi square. So it will become, our purpose is to get C, so C will be F times 5 Fermi. Fermi means 10 to the power minus 15 square divided by e to the power minus 5. This can be further written as C equal to F into 25 into 10 to the power minus 30 into e to the power 5. And the value of e to the power 5 by using calculator, we will get 148.41. So this will become F times 25 into 10 to the power minus 30 times 148.41. Let's keep it as equation number 1. Now, we have to calculate the force between two protons when they are at the separation of 5 Fermi. So we can easily do it. F equal to 9 into 10 to the power 9 into charge on proton 1.6 into 10 power minus 19, 1.6 into 10 to the power minus 19 divided by separation is 5 into 10 to the power minus 15 square. So if we put this value here, so we will get C equal to 9 into 10 to the power 9 into 1.6 into 1.6 into 10 to the power minus 38 divided by 25 into 10 to the power minus 30 times 25 into 10 to the power minus 30 into 148.41. Now these two terms will cancel out and we will get it around 34193.66 into 10 to the power minus 30. We can shift decimal from here to 4 places backward. So this will become 3.42 into 10 to the power minus 26. And we have already obtained the unit of C, that is Newton meter square. So that is our answer. Thank you for watching.